All right, so welcome back to Advanced Track. I hope you all are having a good week. So we're actually done with our theory workshops at this point, and this workshop is going to be dedicated entirely to PyTorch, which is a deep learning library that we're going to be using for our guided projects. So I hope everyone has the Anaconda distribution installed. So I think some of you guys have a little of trouble creating a virtual environment. So that's what we're going to do before we start any coding. So I hope you guys can see my terminal. If you're using Windows, then just use the Anaconda prompt instead and follow what I'm doing on screen. So okay, let's start by creating an environment. So I'm just going to name this, I guess, advanced. And I'm also going to be using Python 3.9. Okay, just bear with me for a second because this is going to take a little bit. Okay. Yes, yes, say yes. All right, I'm gonna actually pause here for a second just for everyone to catch up. Once again, this is the command that I just typed in. Okay, so someone asked why do we need the virtual environment again? So I think, so I guess a way to rephrase this question is why don't we just install like all our packages in the base environment? So the answer is like, because like if you're doing like two different projects, like both of them probably would need like some different like dependencies, like in terms of like package versions. So let's say if you're doing like a project on neural nets like a while ago, and then you installed a version of PyTorch that is like older, and then now we're asking you to install like a newer version of PyTorch. So if you import Torch in your Jupyter notebook, like Python would actually like get confused about like which word version it should install. So creating a virtual environment is just basically a way for us to like be more organized about our packages. If we actually, like, does the doc tell you guys to create a virtual environment? Or am I tripping here? But yeah, if you create a virtual environment, then you can just chill, I guess. So I'm just doing this just so like everyone has the virtual environment like configured and ready to go when we start coding. All right, so notice how I'm still in my base environment here. So I actually have to activate my virtual environment. And then when we just create a virtual environment, it has nothing in it. So we're gonna have to install some packages. So let's do Torch first. Okay, let's see. Ethos runs command conda create. Okay, yeah, that's basically how you create a virtual environment. So I guess if you have all the packages installed already, then you can just go ahead and, I guess, boot up Jupyter Notebook. But now I'm just showing you guys how to like install all the packages that we need for this workshop. Okay, so notice how NumPy is also being installed here, so that's pretty neat. So next we're going to install Torch Vision, which contains the MNIST dataset. Okay, so next I think we have to install matplotlib. And last but not least, let's install Jupyter Notebook. Yep. Those are all the packages that we need. All right. I think now we're ready to boot up Jupyter Notebook. All right. So let's actually start with a brand new notebook. And these are all the packages that we want to install or import. My bad. I'm gonna put these in chat. Oh wait, I'm doing this in waiting room. Hold on. Yeah, I'm gonna actually pause here once again. It's just for everyone to catch up. Feel free to give me like some confirmation if you're done, just so I know like roughly how many people are done. I guess you can react with a clap. Oh, not done. Okay, I'm gonna pause here for a few minutes maybe. If you have any like questions, like feel free to unmute.
So for the Jupyter notebooks in the past, I've used like in VS Code, I made a what's it called, an IPYNB like file. Is that the same thing as what we're doing here?
Yes, pretty much. Except you can just I think create a new like Python 3 file in Jupyter without explicitly like adding the extension of a IPN. Okay, I forgot what the extension is, but it's basically the one that you just said.
Okay, got it.
Yeah, so I noticed a lot of you guys are not ready yet. So if you run into any like issues, like feel free to let us know. We can help you with that. Okay. I think I see where the confusion is. So what I did was I created a new virtual environment. And then what I did is I created a brand new notebook on Jupyter instead of like, so alternative would be downloading the notebook that we gave you and then like opening it in Jupyter. But what I'm doing is I'm actually like starting a new notebook, but I guess you can also use the Colab as a reference. I think that's mainly for people who come in late, just so they have like a kind of a starting point. But ideally, you should probably like start a new notebook with me. Oh yeah, make sure you actually like activate your virtual environment. Okay, here's the commands that I typed, just in case anyone missed them. I guess I'm just gonna have to keep waiting until I get some kind of confirmation. Okay, one person is done. 2 people are done. Okay, I think, okay, a lot of you guys are done. Okay, cool. Is anyone not done? Okay. All right, so I'm just gonna get started then. So let's run this cell. It's taking a while. Okay, finally. Okay. So let's start by creating a tensor. So what is a tensor? So tensor is basically just a you can think of it as a multi-dimensional array, or not array, matrix. Okay, I'm just gonna create a random tensor here. Oops. And yeah, let's print y. So yeah, this is one way to initialize a tensor, is just by explicitly like typing out all its values. But there's actually, if you want to create a tensor of zeros, there's actually a shortcut. You can actually use torch.zeros and then pass in the dimension that you want this tensor to be. Actually, I want to print it out. Okay, so this is what I get. As expected, this matches the dimension that I passed in. So another way to create a tensor of ones instead is by using torch.ones, and then you also pass in the dimensions. So yeah, we get a tensor of ones instead of a tensor of zeros. And there's actually yet another shortcut that you can do to create a tensor of random values. And so notice how all these entries here are random values between 0 and 1. So this is this comes in really handy when we're trying to initialize the weights of our neural network, for example. So yeah, anyone have any questions, or feel free to keep asking questions in the chat if you aren't done. Yeah, if you're behind for some reason, yeah, feel free to let us know. We can definitely help you with that. Also, if you have any questions regarding to creating, with regards to what we just did here, also let us know. Because like this workshop is meant to be more interactive than some of our theory workshops. So yeah, I'm just gonna move on if no one has any questions. So a useful thing that you can do in Python is you can actually, or PyTorch, I guess, is you can actually reshape your tensors. And this is particularly useful for the pre-processing step. Okay, what is the difference between a tensor and an array? So a tensor is more like a multi-dimensional matrix. So a tensor is the term being used in Torch. So there's actually no such thing as an array in PyTorch, but in NumPy, like everything is called an array, or yeah, it's called a NumPy array. So these are kind of just like different terminologies, but they kind of mean the same thing because you can create like a multi-dimensional array as well in PyTorch. No, NumPy, my bad. But like strictly speaking, tensor is a multi-dimensional matrix. All right. So yeah, like I said, reshaping is a very useful thing to do during pre-processing. So let me create another tensor. I guess I'll just kind of initialize this randomly again. And then, oops. So this is what we get. So notice how this matches the numbers that we type here. So that's expected. Now I'm actually gonna print out the size of A. So this is 2 by 2. And we're actually gonna try to reshape it now with torch.reshape. The first argument here is just the tensor that we want to reshape, and the second argument is the dimension after the reshaping. So I'm going to reshape it to be 1 by 4. And as you can see, we're effectively concatenating. We're basically taking the second row here, and then we're concatenating it to the first row. So let's print out the shape of B. So as you can see, the dimension here is 1 by 4, which is what we passed in. So that's good because that's expected behavior. Okay. Someone have a question? Okay. Never mind. Okay. So another thing that we can do is we can actually flatten this tensor with torch.squeeze. Can't spell. So this actually looks like very similar to this, but notice how there are 2 brackets here and there's only 1 bracket here. So let's actually print out the dimensions here. So notice how B has size 1 by 4, but C has size 4. So what we're doing here is we're basically flattening B and taking away one of its dimension without losing any information. So that's the key. So if we try to do something like flattening A, for example, you can see like nothing happens because you can't really like flatten this tensor without like losing information. So this is still 2 by 2, which is the same as A. So yeah, that's basically how flattening works in PyTorch. Does anyone have any questions? If not, I'm going to just move on to some basic operations that you can do with tensors and PyTorch. All right, so let's create yet another tensor. Guess I'll just create this randomly again. I'm actually gonna print out the size here. And then I'm gonna create another tensor with the same dimensions. All right. So there's some activity in chat. What about x by 1? Oh, okay. So let's actually test this out. Insert another cell. Let's see. So I guess I want to reshape A to be 4 by 1 instead. Okay, so we have a tensor that's 4 by 1. And let's try to flatten it. See what happens. So yeah, once again, we end up with the same results as we did. Because we're basically, so you can think of, what was it? B as like, I guess a row vector, because it has 1 row and 4 columns. And E is basically a column vector. And so after we flatten both of these, we basically end up with the same thing. So I hope that makes more sense. Can you print out F? Yes. Let's see. So yeah, this is exactly the same. Just as I explained, I guess. All right, cool. Hope that makes more sense. Okay. Okay, so I'm just gonna move on to some basic operations that we can do with tensors. So notice how X and Y has the same dimensions. So what we can do here is we can actually compute the sum of these two tensors. As you can see, we're basically just adding them up like element by element. So there's nothing really special here, I guess. So another thing we can do is we can take the element-wise products of these two tensors. And so, yeah, I think there's nothing mystical really happen here. We're just taking the element-wise product. Hopefully everyone is good with this. So notice how like these two tensors have the same size. So that's the reason that we can do these two operations. So I'm actually gonna, I guess, redefine Y here in a way that would enable me to do matrix multiplication. So just bear with me for a second. I actually missed a bracket. Okay. Let's print out the size. So notice that the second dimension of X matches the first dimension of Y. So that means we can do matrix multiplication. So we can do this by using matmul. And then notice, so keep in mind that the order here actually matters because we're doing matrix multiplication. So yeah, this is what we get. And let's print out the size. So this is 3 by 5, which is as expected because it has the the first dimension matches the first dimension of X, and the second dimension matches the second dimension of Y. So this is expected. All right. So I'm gonna wait for everyone to catch up. If you have any questions, yeah, feel free to type in chat. Or if everyone is good, yeah, feel free to give me like a thumbs up. All right, we have 1 thumbs up. I'm gonna wait for, I guess, like 30 more seconds. Does Hadamard symbolize something different from regular matrix multiplication? Okay, yeah, so let me explain this in a more clear manner. So when we do X asterisk Y, we're taking the Hadamard product, as someone has pointed out. Okay, I spelled this correctly. So what we're doing here is we're taking the element Y's product of each entry in our tensor. So the reason I can do this is because the dimension here is the same. So that's why I can multiply each element here 1 by 1. So matrix multiplication is different because in order to do matrix multiplication, we want the second dimension of X to match the first dimension of Y. So that's why I have to redefine Y here in a way that can enable me to do matrix multiplication. So yeah, I guess, yeah, I think the confusion is coming from the fact that I redefined Y here without, I guess, explicitly saying so. Maybe I should have used another variable name, but yeah. So hopefully that clears up some of the confusion between matrix multiplication and the Hadamard product. Okay, I think I'm just gonna move on here. So another interesting feature that you can do in PyTorch is called symbolic differentiation. So this is basically just like, we're basically, okay, did I spell this? I may have spelled this wrong. That's embarrassing. Hold on. Sorry, I was a little bit distracted. So what we're doing here is we're basically, okay, let's actually do an example here. So I'm gonna create yet another tensor. So I think we actually have to make sure this says floating point values here. And then we're gonna set the requires grad argument here to be true. The default value is false. So by setting this argument to be true, so what we're doing here is we're telling PyTorch that we want to compute the gradient of this tensor in the future. So PyTorch would actually record like every operation done on this tensor in order to compute its gradient. So this is also called symbolic differentiation or automatic differentiation. So now we'll actually perform a few operations on X. So we're gonna square it element wise, and then we're gonna be taking the sum. And then I guess I'll just store this in the variable called out. Whoops. So out here is just equal to 4. So this should be fairly self-explanatory because I'm just squaring every element in this tensor and then adding them up. So what we can do here is we can actually do back propagation without here. And then after we do the back propagation, we would actually, yeah, X would actually has some gradients available. Okay, so how do we get, to -2, 2, and 2? So this is actually a great question. I'm gonna try to show you guys how we got that. So out is basically just x1 squared plus x2 squared plus x3 squared plus x4 squared. So this is a pretty simple function, I would say. And so when we differentiate out with respect to, I guess, let's say x1 for now. So what we get here is 2x1, right? Which is why the first entry here is a 2, because it's 2 times x1, which is 1. And so if we do this for x2, we get -2 because x2 here is a -1 instead of 1. So yeah, we can do a similar thing with x3 and x4. So hopefully this explains how we got the gradient here. So I think we have some questions that I'm gonna take. Can you repeat what backward does? So out is basically a function of x. So when we call back propagation on out, we're back propagating the gradient back to x. So that's why we can access the gradient of x after this step. So what actually goes on under the hood is PyTorch is recording all the operations done on the tensor x, because we are saying the required grad parameter to be true here. So that's how PyTorch is able to keep track of the operations that we have done on x. And this is how it's able to compute this gradient here. Yeah. So there are actually like 2 ways to do sum, as some of you have pointed out already. So you can do torch.sum, or I guess a tensor.sum. So I'm just using the second version because it's shorter, but yeah, I think in the Google Colab, the other version is used. So yeah, any more questions? If not, I'm actually going to be passed on this to Adithya, who's going to go over how to load a data set in PyTorch with you guys. So yeah.
Yeah, cool. Let me share. All right, can everyone see my screen?
Yeah, I think you're good.
All right. Good stuff. All right, so let's talk about loading in custom data sets. I mean, let's talk about just loading data sets in general, but let's start off with talking about custom data sets. So PyTorch is a super powerful sort of package. But when we feed in data or data from a data set, in order to use a lot of these cool features like the autograd thing that Jenson just showed us, we need to supply that data in a form that PyTorch essentially understands. So that would involve us to really just define certain methods that can act on this data set that aligns with certain guidelines that the PyTorch module sets for us, which I'll show you like right now. So let's begin with define a data set class. So here we go. I don't know if you guys are going to be too familiar with defining classes and stuff in Python, but honestly, just follow along with me. And if you have any questions, don't hesitate to like put in chat or unmute yourself. Anything works. So yeah. So we first define the class that will hold our data set. So the way we do that is again class, and then we specify the name, the custom data set. And this custom data set needs to inherit from a predefined class that PyTorch has already defined for us. So and that data set is, I mean, that class that PyTorch is defined for us is torch.utils.data.data set. And so essentially inheriting from this this predefined class from the PyTorch helps PyTorch begin to understand the data set that we can that we're going to be passing into this class. So essentially just think of what we're doing right now as creating a sort of structure, a sort of box that we can use to pass in data about passing data about our data set from our data set, and then also define certain functions or methods for that data set to maybe like get items from that data set or find the length of the data set, which we're going to see right now. So the first things first is we have to define a constructor, and all constructors in Python have this sort of syntax: underscore underscore init underscore underscore. And yes. So what we're doing here right now is, so this is a little weird thing with Python and classes in Python. For every single function that you define for a class in Python, you need to pass in this first parameter, which is always self. Self is just an instance of the class you're defining. If you're more used to doing C++, which if you are, I mean, you should be if you're doing CS at UCLA, is C++ also technically passes in an instance of the class into the methods you're defining. It just does it implicitly. But here in Python, you have to be explicit about it. It is what it is. Statements is, you can think of statements as our actual data, our inputs from the data set. And you can think of truth as our labels for all those inputs. So yeah, so we just need to go ahead and assign self.statements and self.truth, just like that. And what this is going to be doing is we've now essentially assigned our custom data set attributes, statements, and truth, those two attributes to be the input that we pass into the class when we call the constructor for that class. So yeah, any questions about anything that we've done up till now? I actually don't know where my chat box thingy is. I can't find it. 1 second. If there are any questions. Where is my chat box thingy? Okay, what else? Oh, there it is. Cool. Oh, there are things. All right, where did? All right, yeah, there's a few things going on that I missed out because I didn't see chat. Yeah, so yeah, the cool thing about Python is when we inherit from this class, yeah, it automatically calls the default constructor for super class exactly. So we don't have to we don't have to worry about it at all. I think I might be wrong, but I think you only explicitly call the superclass so when we need to pass it some parameters. But otherwise, I think it's called implicitly. Might be wrong, but in this situation, no need to call the you don't need to call super. So yeah. All right, let's move on. So the next thing we need to do is, in order to follow the guidelines that PyTorch kind of sets for us, we need to define two more functions, at least for now, which is get item. And it follows the same format as init, where you have two underscores before and after get item. And again, once again, we pass in self, which we have to for every single method in the class. And then we also pass in index. And what it's going to let us do is it's going to let us call this underscore get item underscore method when we create an instance of this class, and essentially return what the input and label is at that index. So the way we do that is self.statements index, and then self.truth index. All right. So what this is doing is, and this is one of the neat things about Python, is you can kind of just return anything that you want from functions. So here we are returning a tuple, which is a collection of two values. And essentially what it's doing is it's parsing through our statements and our truth, which are essentially our inputs and our labels. And it's finding the values that are at the index that we specify as a parameter when we call this get item function. And we're going to see this in action when we actually create the instance of this class. So yeah. And finally, we have one more thing that we need to define, which is what is the significance of underscore name? We are not using underscore. Oh, the underscore. Oh, okay. That's just the syntax that PyTorch expects from us. It is what it is. I also believe, there are certain guidelines that PyTorch sets for us in order for it to understand these sort of custom data sets that we define. You will need to implement methods that are named like this. Yeah, I believe so. Cool. And then finally we have in C++. Yeah, honestly it's all about just like syntax. Right, this syntax is the one that PyTorch expects from us when we define these functions, because PyTorch itself is going to implicitly use these functions that we define here in order to do all these things like getting a particular item or finding the length of our data set. So when PyTorch calls these, it needs to be able to recognize these methods, and that's why we name it like this. So these aren't like member functions that we'll use. Well, we can use them. We can call these member functions and get the same result, but it's more so for PyTorch. I don't know why I keep calling Python, but it's more so for PyTorch to use in order to, for it to recognize the data set, create batches, all that sort of stuff. And we'll see how it works once we finish defining this class. So yeah. All right, and then finally we'll go ahead and create the Len method. And again, this one just requires the self parameter, and we're just going to go ahead and return len of self dot truth. Cool. So this is essentially our custom dataset class. It's very simple, but it does what it needs to do. We're initializing it. We're bypassing it an array of labels and a corresponding array of we initialize it by passing in a custom not custom, but like an array of input and a corresponding array of labels, and we define a get item function, which lets us index our input and label to get the corresponding input and label for some particular index, and we also define a function to get the length of our data set. So yeah, we can go ahead and execute that, and we can move on. So let's begin by defining a dummy data set. So let's go ahead and just set up a list of inputs, which is going to be essentially our statements. So let's see. Avocados are the superior fruit, and maybe apples are oranges. So that's our set of inputs. Essentially our input values that we want to put into this data set. And then we can define our labels. And the first one is obviously true. And the second one might be false. So JK, it is false because duh. All right, and then we can go ahead and initialize an instance of this custom data set by calling the constructor. So we can go ahead and do custom data set, and then we have to pass in inputs and then labels. Cool. And that essentially creates a data set for us, passes in the inputs, sets the attributes of the fruit data set object. So now it holds these inputs and labels. Obviously, in reality, when we deal with a bigger amount of data, it's not just going to be this small, but it's essentially the same thing. And this is a good opportunity to kind of show you guys how these sort of methods work. So we can go ahead and call fruit dataset dot underscore get item underscore of 1. And that should ideally return to us apples or oranges and false, which we will see if it does in a second. And then we can also go ahead and print fruit dataset dot underscore len, which should oh wait 1 second, this is supposed to be parentheses, and also fruit data underscore length. Let's see if this works. So yeah, it's exactly what we expect to get. Apples or oranges and false because that's the first index. Yeah, keep in mind we're using parallel indexing for our inputs and labels. So that means values that are in corresponding indexes refer to one another. So that's why avocado is superior is true, apple or oranges are false. So that's why we get that over here, apple or oranges and false. And then the length is 2. So essentially this is what PyTorch is going to use when it helps us to use all these cool features that PyTorch provides for us. All right, so now let us go ahead and create something known as a data loader. So yeah, before we go do that, what is the difference between a data loader and a data set? So for data sets, we define classes that hold these data sets and have these methods that can work on this data set object. Data loaders do exactly what is in their name. They load in data. And this is how we can, create batches for our data. It helps us, to break down the data that we already have, load it in, and pass it into our model when we actually train the model that we define. So let's see. So when we create a data loader, it's fairly simple. You just go ahead and call it like fruit data loader. And we're using one because we're gonna declare a few more data loaders and see how they work. And the way you create these data loaders is by calling torch.utils.data.data loader. And data loader accepts a lot of parameters, but right now we're gonna focus on just 3. We're gonna go ahead and call, so the first one is our fruit data set. Fruit data set object that we declared like in the previous cell. We also want to specify what the batch size is going to be. So right now we'll just say that it's 1. And then data loaders also let us shuffle the data around so that we don't have to do that explicitly ourselves. When we use a data loader, it'll go ahead and automatically shuffle the data for us when we want to train and test our model. Cool. So what this lets us do is, and don't worry about the syntax in this for loop I'm going to use. It's not, super convoluted or anything, but essentially what we're doing is we are, see, we're tapping into this fruit data loader, which is essentially iterable, which means we can loop over it. And then we can also print out the data. So when we run this, what do we expect to see? Invalid syntax, apparently. Because I'm an idiot and I forgot that. So why does this output make sense? Let's take a look at it like this. We have I, which is essentially just telling us what the index of the corresponding outputs are. So the number of times the for loop has run, essentially. But it's this data value that we are more interested in. And what this data is it is extracting batches from this fruit data loader and giving it back to us. Since we define our batch size to be 1, it's only giving us batches that are, well, which only have 1 sort of input and label. That's why you see 0 and 1 here. But however, if we go ahead and redefine these, call fruit data loader 2 and maybe call a batch size of 2 instead, and run that. Oh, sorry. Then you can see we only get one data point back. Instead of 0 and 1, we only have 0. And in this 0, our data here contains 2 inputs and 2 labels, as you can see here. And the reason for that is because we specified it to have a batch size of 2. And you can vary this for the for whatever your purposes are. Since we only have 2 data points, I keep calling them data points, but 2 inputs and 2 labels. That's why we're limited to a batch size of 2. But if you're dealing with huge amounts of data, you can specify bigger batch sizes, and you would get the output in a similar format. And this helps us when we're training our model, and we want to pass it in data, and we want to create batches and stuff. These data loaders are super helpful for that. Okay, cool. So that is that's custom data sets. Are there any questions before I talk a little bit more about loading in data sets that are not custom? Why is the only values in Tensor? Yeah, so PyTorch automatically casts these in tensors. And I think the reason for that is because it recognizes these false and true as essentially zeros and ones. And it realizes like, oh, I can go ahead and cast these as tensors because PyTorch essentially works off of tensors. Everything in PyTorch, all the data that we handle is needs to be a tensor. If you think about it, oftentimes when we're creating these data sets, we don't really use strings, which is why PyTorch wasn't able to really cast it into a tensor. But for false and true Boolean values, it could be casted, and PyTorch automatically did that for us. In reality, our inputs are more or less also going to be numbers, and PyTorch will cast them into tensors as well. Any other questions? All right, we will move on, make it super quick so we can get into the more interesting stuff, which is actually creating our neural network. So so if you guys remember the MNIST data set from, I don't know, week 1, week 2, the first workshops that we did, we had this data set consisting of like all these hand-drawn digits, these 28 by 28 pixel hand-drawn digits. And we could use a feed-forward neural network on them to essentially classify those digits as between 0 and 1. Yeah, the MNIST data set. So we're going to be using that same data set. We're going to create a feed-forward neural network to essentially classify them with a pretty high level, pretty high accuracy. So let's begin doing that. We'll go ahead and begin by creating a trained data set and a test data set. And the way we do that is we're going to use this Torch Vision library that we installed previously. And we're going to call this torchvision.dataset.mnist. And we will be passing in a few parameters that I'll be explaining to you in a bit. So yeah, bear with me here for a second. Okay, so it's a fairly long list of parameters, but let's go through it one by one. Let's ignore the first one for, is this a standard data set in PyTorch? It's from Torch Vision. I'm not too familiar with PyTorch exactly. So I don't know if Torch Vision is related to PyTorch in any way, shape, or form. So if anyone else wants to chime in there. But I'm assuming it is because it has Torch in the name. So yeah. So yeah, you can think of it as pretty much the MNIST data set is from, it's essentially like a standard data set from PyTorch, as it should be, because MNIST is the first thing you often do when you're dealing with neural networks. So yeah. So the first, let's ignore the first parameter for a second. We're calling train equals true because, yeah. So we're saying train is equal to true because in reality we can specify if we want the training data set or the testing data set, and the train data set will have a lot more data we can use to train our model. So we have to specify train is equal to true to get the training data set. We call this transform. Well, model source vision, no attribute data set. Oh, well, that's problematic. I'm gonna assume that's probably because either Torch Vision was not installed, or you probably installed a version of Torch Vision that might be too old.
I think it should
Wait,
work
give
if
me a
you did pip install Torch Vision like I did like earlier in the workshop. But yeah, make sure you spell data sets instead of data set. So there's an S there, so that could be the
Oh yeah,
reason
that's
as well.
also true. Make sure it's data set and not sets or anything of that sort. My bad. It is data sets. I might have missed that out, but it is, yeah. Don't forget the S. My bad. I did not. I kind of forgot to put that in, but it should work if you put data sets.
Can you try to run this cell?
Okay, cool. Yeah.
Okay, cool.
Yeah, small details to keep in mind. Cool. We have this transform parameter, and what this does essentially is pretty explanatory. It takes our inputs and converts them into tensors so that they can be worked with, so they can work with PyTorch. And this download equals true. So whenever download is equal to true, that's telling this method or this constructor at least that, oh, I don't have this data set, this MNIST data set. So I want you to download it. That's why you said download equals true. And what that does is it actually places that into this /data directory that we specify. So that's how this and these two parameters are related, the first one and the last one. If you actually specify it as download is equal to false, what we would do here is it would actually look in this specified directory over here for the data set that we want to load in. But in this case, we actually don't have the data set, so that's why you want to specify download equals true. So we're going to head and copy this and do the exact same thing, but now for the testing data set. So we're just going to go ahead and call this test data set. We will not specify this because now we want the train is by default false, so we can just not specify it and it'll give us back the testing data set. And everything else pretty much remains the same. So running this should, if you not run this already, it should give you all these pop-ups or whatever they should be called, saying like, oh, it's downloading all the data set. And now you should find in the directory you're working in a folder called data, which contains an MNIST folder, which contains all the testing and training data. So yeah. So cool. And let's go ahead and yes, let's move on. Are there any questions before we move on? Okay, doesn't seem like it. All right. So the next thing we can do is declare an iterator. And what this is going to do for us is it is pretty much akin to creating an iterator in C++ for like a vector or a linked list or something. It essentially lets us iterate over our data, our training data. So fairly simple, we call train iterator equals iter and train data loader. And what this lets us do actually is it lets us extract batches from our data loader by essentially calling train iterator dot next. So it's pretty similar to how an iterator for a vector in C++, if you guys have taken CS32, you can kind of do like iter dot, I don't know if it's iter dot next, but it's very similar to that where you can like, oh no, you just like increment the iterator. But yeah, here you can call dot next on this iterator object, and in order to like extract different batches. And so what we can do is we can do like inputs, comma labels, and we can extract that from this batch of samples. Right. And so yeah, what that does is so train iterator.next essentially gets a particular batch of samples, and then it separates it out into inputs and labels. So in this case, we expected input to essentially be a 28 by 28 like matrix of pixel values, which is what the MNIST data set was, all these hand-drawn digits. And label should be essentially the number that it is classified as. So we can go ahead and quickly visualize data. I'm not going to spend too much time showing you the code for it because we're more interested in actually seeing it. But visualization is important, and this one is using matplotlib, which isn't necessarily the focus of today's workshop, but it is a cool skill and package to get into a bit more. But essentially what we're doing here is we are, yeah, that's the code right there that Sudhanshu put in. All it's doing is not printing out, but like showing the values, those pixel values in a 28 by 28 grid. Running this, oh, train data loader not defined. Why is that? Oh, dear me, I kind of forgot to even declare those train data loaders. Yeah. So before we even iterate over the train data loader, we have to declare those train data loaders using the training data sets, which I completely forgot to do because I'm smart. But the way you do this, creating the data loaders is very similar to how we did it back up here when we were using it for the fruit data that we defined for a custom data set. It's just the same thing. We do torch.utils.data data loader. And again, the same parameter that we used up here, the actual data set, the number of batches we want, and whether we want to shuffle the data. So obviously, the data set is obviously the trained data set. The number of batches, let's say we want batch sizes of like 16 maybe. I think that sounds good. And let's go ahead and shuffle our data. And we're going to essentially do the same thing, but also for the test data set, because we define two data sets for both testing and training. Run this and run this. Jesus, okay. Lowercase s, guys. Okay. But yeah, so what we can see here right now is it gives us a nice picture of a 1, which is the hand-written digit. And as you can see here, it is this 28 by 28 grid. It has a 16 by 1 because we specified that we want our batch size to be 16. And so we have this batch size of 16. We're essentially looking at the first value in this batch, and that value is a 28 by 28 grid of pixels. And the label is essentially 1, which makes sense. So yeah, running this again, actually, as you can see, it's actually showing us a different thing now. And the reason for that is we're actually calling .next. And this .next is doing exactly what it does. It just moves on to the next data set. Sorry, data sample. And as you can see here, it's a 7. Running this again, it's a 6. So yeah, it just kind of keeps on specifying all these different data, essentially the hand-drawn digits. But yeah, that's about it when it comes to actually loading in data sets. There's a little bit more to it because you kind of need to specify all these different parameters, define your own classes for custom data sets. But hopefully everything made sense. And yeah, are there any questions before we move on to like the next section? Cool. All right, well, in that case, I will hand it over to Sudhanshu, and we'll talk about how we actually go ahead and implement the neural network that trains, that will train on this data set.
Cool. Can everyone see my screen?
Yeah.
Yep.
Awesome. So yeah, so at this stage, to quickly recap, we have all our libraries, we have our data set, and now the point is to create a neural network and actually train it. So what I've written here in this markdown cell is what I want my neural network architecture to be. So this is something we just came up with randomly. We're essentially going to have two hidden layers, one with 256 units, which is a ReLU layer, another one with 128 units, which is ReLU, then an output layer, which is softmax. And finally, our loss function is going to be cross entropy. So this is the planning phase. This is what my neural network is going to look like. And the way we define our neural network is the following way. We need to define it as a class. So when we did our custom data set, we also defined it as a class. And this is kind of a common theme in PyTorch. Everything is a class. So we're going to define our model as a class. So we're going to say class model extends nn.module. So this is the library. So this is the class from which the model class. This is a sorry. This is the class from which the neural network is going to be inheriting, nn.module. And again, we're going to have to implement the init function, which is the constructor of the class. So I'm going to say def init self. So the parameters that the constructor takes is actually the number of features that are in your input. So if you look over here, these are the number of samples in the batch. So let's ignore that for a second. But each training sample contains something which is 1 by 28 by 28. 1 by 28 by 28. So what we're going to do when we're training is we're going to take this, this 28 by 28 array and flatten it. So we're going to squeeze it and make it one long vector. So 28 times 28 is 784. So I'm going to make this a little more general. I'm going to say my neural network expects some input dimension which is passed in. We have a question here. Would you ever expand before compressing? Like 784 to 1024 to 256? It would depend on the application, I suppose. I don't see the purpose over here. Usually, like upsampling, would result in loss of information. I mean, you don't have that much information, so it might not help in this case. But I could see architectures where that helps. I think we actually covered one of those in the theory workshops. But yeah, so we're going to take some input dimension and we're going to take some output dimension, which are the parameters of our neural network. So it's just saying the neural network expects input of this dimension and is going to throw an output of this dimension. Simple as that. Okay. And just to be slightly rigorous and adhere to some old Python, I'm going to call my superclass constructor. Okay. So super.init. That's about it. And now let's get to the actual layers. So in PyTorch, the way a model has layers is that each layer is a member variable of that particular class. Actually, technically, it's a member method of that particular class. So I'm going to define it in the following way. I'm going to say that self.layer1, which means layer 1 belongs to this class, is going to be nn.linear. So linear refers to simply the wx plus b. So actually, let me make that clear. Wx plus b. So a linear model simply takes the x, multiplies with w plus b. And it's going to expect input dimensions that we passed in, and it's going to spit out something which has dimension 256. Okay? Does this line make sense to everyone? What we're doing is essentially defining this wx plus b portion. We'll define the ReLU later. It's not going to be at this stage, but this is like the core parameters of the model right now. Okay, so to see it again, we have self.layer2, which is nn.linear, and it's going to simply take in the output dimension of the previous vector of the previous layer. So 256 becomes now the input dimension, and it's going to spit out 128. Okay, so then we're going to have a third layer. One second. Yeah, we're going to have a third layer, which is our output layer. So again, this is going to be some kind of a linear layer because we see wx plus b. So it's nn.linear, which takes in 128 and spits out the output dimension. Again, I want to note we haven't done any activation yet. We'll be talking about that in the next bit. Okay. Does this make sense to everyone? This way we define layers. Okay. Then the next thing we're going to do is we have a question. So the first number is the number of nodes. No. So in fact, the first number is the input that it expects. So technically, this will be a layer with 256 neurons. So the value that it spits out is the 256 over here. Does that answer your question? Cool. Okay. So the next function that we need to implement, so now we have implemented our init function, which is our constructor. Next function is the forward propagation function. So this function is going to tell us how do we manipulate this x that we get. So our model is essentially just some big function, right? It's a complex function, but what it's going to do is going to take in some x, do some operations, and spit out some y value. And the forward function tells you how that's done. It's the forward propagation function. So I'm going to take my x, and I'm going to update it in the following way. I'm going to say f.relu of self.layer. Actually, let's make this even easier first. So the first thing I'm going to do is I'm going to take my x, and I'm going to pass it through layer 1. Okay. So all this is done is passed wx plus b. Once that's done, I'm going to pass it through a relu. Does that make sense? So it's exactly like the formula over here. It's relu of linear. Okay. So after that, I'm going to pass it through layer 2. So it's the exact same thing, self.layer 2 of x. So this x goes in here, produces this. Then it goes in here, produces the new output. Okay. So the next thing I'm going to define is my output layer. And we want to be a little careful here. This is the thing about PyTorch in particular. So I'm going to do the same thing initially. I'm going to say that x goes to self.layer 3 of x. Now that's implemented this wx plus b part over here. But what we also want to do is apply the softmax. Now we're not going to actually apply the softmax right over here. So in PyTorch, we're going to apply it in a different position. So all we've done until now is we've done this, this, and all the way up here. Softmax is going to come later. We're not going to define it over here. So essentially, we're done. We're just going to return this x, and we're done. That ends up being the structure of our class. So to recap, all we're doing is defining what our layers are and defining what the layers do to our x. Okay. Are there any questions about this? Is everyone pretty much clear on this? It's like something you're gonna, I mean, every time you define a new model architecture, this is what you're gonna have to redefine. Okay. I will assume everyone is good to go.
Can I ask one quick question?
Yeah, absolutely.
So sometimes I think we mentioned like some layer or some types of neural networks will keep passing through the same layer multiple times. So if that was the case, and I know this is a simpler model, but would we just keep specifying to pass through the same layer?
Keep passing through the same layer. I don't understand what you mean by multiple times. What do you mean by that?
So I think like in, for instance, the CNNs, we talked about like reusing a layer. And so the data would keep cycling through that layer, like let's say 5 times, and then you'd pass it on to the next portion or whatever. So for instance, I forget what it was called. Sorry, I'm trying to find it in my notes.
In convolution and max pooling?
Yeah, exactly. So you have to run that multiple times before you pass on to the next segment. So if that's the case, do you have to define multiple layers, or can you reuse the same layer?
Actually, you have to be a little careful because, like, I think every time you do max pooling, you're basically downsampling your feature maps. So I think you have to readjust your dimensions.
Yeah, that's a good point. And I think another point, right? So each of these layers has its own W and B associated with it. So we can't reuse this layer because it has its own W and B associated with it. And these W's and B's are what we're going to like optimize over later on, right? So we're going to actually update these layers later on. Does that make sense? Because I can't say layer one, because it's gonna say that, oh, you have only one set of parameters that I'm optimizing over. Like that doesn't make any sense.
Okay, yeah, I think that makes sense. Thank you.
Okay, awesome. Yeah, so now that we have our model class, we're going to create an instance of it. So I'm going to create my model, and I'm going to say that my model is an instance of model. And if you recall, we need to pass in the input dimensions and the output dimensions. So in this case, like I said, the input dimensions are this flattened, squeezed vector of size 784. And the output dimensions, well, we have 10 different digits. So our output dimensions are the 10 different classes 10. Okay. And a nice thing to see is, oh wait, I didn't define my thing. If you just run the cell, it gives you a little nice summary of your entire model. So it says layer 1 is this with in features, out features, and it has a bias. So that's a nice way to see the summary. I believe there's a summary function as well. Nope, never mind. Something like that, but there's a nice way to see what your model looks like. Okay. Now that we have our model, we need to choose a loss function. Yeah. So the loss function that I choose is nn.crossEntropy, entropy loss. So it's simple. The nn library has this function predefined, and it passes in. Now I want to make a note right here. The cross entropy function in PyTorch includes softmax. That's why we didn't add the softmax over here, because our loss function includes that softmax function. Okay. And the next thing we're going to do is choose an optimizer. Why am I typing so badly? Choose an optimizer. So I'm going to say my optimizer is torch.optim. And I'm going to say my optimizer is add-in this time. So the optimizer is simply the way you do gradient descent. It could be stochastic gradient descent, it could be ADAM, it could be RMS prop, it could be momentum. Whatever the algorithm you're using, that's what your optimizer is. And we didn't cover ADAM in advanced track, but they covered it in detail in advanced plus. In an abstract manner, ADAM is just a very powerful way to do gradient descent. It's kind of the standard way to do gradient descent. You don't know what to use, just use ADAM. So we're going to define it in the following way. We import it from the torch.optim library. And in PyTorch, the optimizer is what updates your parameters. So when you define your optimizer, you need to actually specify what those parameters are. So at the stage of definition itself. So in this case, the parameters are all these W's and B's that are in our layers. So I'm going to access them in the following way. I'm going to say my model.parameters. So that way Torch knows that these are the parameters that it needs to update. And another argument you can pass is that the learning rate LR is 0.01. So that tells us how fast we want to update. Okay. Yeah. Any questions at this point? Yeah. Yeah. So far we have our model, we have our loss function, we have our optimizer. Any questions? Is everyone more or less caught up with everything that's been typed out? Okay, so the next thing we want to do is actually train our model. So training. And PyTorch has this thing. When you want to train your model, you need to declare it unambiguously that, hey, I want to start training my model. So what this does is just sets like the state to say training is equal to true. Now, full disclosure, this doesn't matter for this particular architecture, but when you do other stuff like dropout regularization or batch normalization, it's actually very, very, very important that you declare this beforehand. So it's always very good practice to have this before you start your training routine. Okay. So the next thing, so to train, I'm just going to create a simple for loop. I'm going to say for epoch in range 10. So for 10 epochs. So an epoch just simply means we have looked at all our data. We have all these batches. We're going to go over all the batches in one epoch. I'm going to say for a batch in iter of chain data loader. So what this is doing, so it's saying for each batch. Simple as that. We have that iterator that we defined earlier, train data loader. We're simply going to iterate over it and pick up one batch at a time. Okay. So we're going to say the batch inputs, comma the batch outputs, batch labels, my bad, is equal to the batch. So this just unpacks that batch, takes the X values, takes the Y values. And I'm going to reshape my batch inputs. I'm going to say torch.reshape batch inputs. And I'm going to reshape it to 16 by 784. Okay. So earlier we had 16 by 1 by 28 by 28. I'm making this 16 by 784. So that way we have 16 samples, each of which is a vector of size 784. Okay, let me pause here for a quick sec. Does this make sense to everyone, what we've done here? We're going to iterate over each and every batch, unpack the batch, and just reshape it. Okay, so the next step is something that's again particular to PyTorch and actually particular to most deep learning languages. And basically what happens, right? Every single time we backpropagate, the gradients accumulate. So let me put it this way. So when we had our, let me scroll up to where we had out. Okay, so when we did out.backward, we backpropagated. So what this does is it doesn't say x.grad is equal to 2. It actually accumulates the value of x.grad. So it'll say x.grad is equal to x.grad plus the new gradient. So in PyTorch, the gradients don't refresh automatically. They always accumulate. And this is actually very useful for like deep learning, but it's not always what we want. In our case, we want a fresh, brand new, shiny gradient every single iteration. So what we need to do, we say that gradients accumulate. So we need to clear them out at every iteration. So the way we do that is simply optimizer.0_grad. And that will zero out all the gradients that are stored. And this is actually very, very important. It's an easy step to forget and will 100% lead to like very weird results. So don't forget it. So there we go. Now what we want to do, we have our inputs. Let's try and make some predictions. The way we make our predictions is simply by evaluating it on our inputs. So we had our model, my model, and we evaluate it on batch_inputs. Okay. The next thing we're going to do, now that we have our predictions, you want to see how good are these predictions. What is the error? What is the loss? So we say that the current loss is equal to loss of predictions batch labels. So we had our loss function that we just defined, cross entropy loss. We simply pass in our predictions and we pass in the true labels. That way we get our final loss. Now that we have our loss, the next step is to, of course, backpropagate through it. We want to find out, what caused this loss to be so good, what caused it to be so bad. And the way we do that is current loss dot backward. This will backpropagate through that loss. So when this step is executed, all those parameters that were just stored inside our model, all of them get that dot grad parameter. All of them have that field dot grad, which is now updated and contains the gradient. So the next step, once we have our gradients, is simply to perform our optimizer step. So this could just be a gradient descent step, it could be an Adam step, RMS prop, whatever. It just performs that one gradient descent step. So I don't know if whoever attended like beginner track and stuff, it's just simply, x new is equal to x old minus learning rate times grad. In the vanilla gradient descent case, of course. Okay, and I'm gonna define something, a nice printing function, just so that we see what's happening. I'm just printing out the loss at every iteration. Okay, so does this training routine make sense to everyone? It's a good time to pause for some questions. Okay. So no questions. Okay, I'm going to let this model train for like one epoch. I'm not going to train for all 10 epochs, just to make sure it works. So let's give it a second. It should hopefully print something out for us. And yeah, ask any questions in the meantime while we wait for this guy to train.
So when you say 784, is that 28 by 28, or is that like a 1 by 784?
It's 28 by 28. So wait, could you repeat the question? I don't understand the distinction.
I just want to understand the shape, like the format of the matrix or tensor or whatever we're using to store that data.
Right. Okay, so 16 firstly refers to the 16 different samples, and each sample has a size 784.
And that would be each pixel.
No, so 784 refers to all 7084 pixels. 28 by 28 is the 784 pixels.
Got it. Okay.
Okay, cool.
That makes sense.
Yeah, so our loss seems to be, our model seems to be training, thank God. So I'm just going to kill the execution. You can do that with this top button over here, okay? The plus button here, okay? So something happened. We don't know how good it is. So now we want to test our model out. And again, when we did our training, we had to declare that we are training our model. Similarly, when we test, we need to declare that we are evaluating our model. Again, this is an important line. Please don't forget it. It's going to cause problems later on in life. So always remember this one. I'm saying from experience. I've made this mistake before. So please remember to put this line. Okay. And I want to show you how we can try to evaluate our model. So if you recall, we had some inputs that we defined earlier, way back here. Oh, why is this indented? Okay. We had some inputs that we defined over here, right? And all I'm going to do, I'm going to pick out the first input and I'm going to reshape it like we did over here. So I'm going to say torch.reshape this input to be 1 by 784. Okay, 784. So instead of 16, because I have only one sample, it's going to be 1 by 784. I'm going to say this is my IP input. And I'm going to say my prediction is my model evaluated IP. Let me see what this prediction is. As we can see, it's a tensor that contains 10 different values, which is very good, which is exactly what we expect. So each of these values represents the the probability or the confidence that the digit at this location is the true digit for this particular input. And what do we want to do? We want to actually pick out the maximum value amongst all of them, because that's the one we're most confident about. So just glancing at it, it looks like this is the largest one, I think. So we're going to extract that using argmax. I'm going to say axis equals 1. You'll see why later. Don't worry too much about that. And let's try and actually just plot what this image looks like. This is the same exact plotting code that I used before, so don't worry too much about it. Prediction pred.item. Okay, awesome. So turns out it worked well. Even after one iteration, we got the correct result, which is awesome to see. And what essentially happened, we got that big tensor. We picked up the maximum value using argmax. Actually, let's be more specific. Argmax picked out the index at which the maximum value occurred, which is what we want, because we want to find out which digit produced that maximum value. And I just plotted the image along with what our prediction was, and in fact, it was 8, which is awesome to see. Okay, so does this make sense to everyone, how we evaluated our model? It's pretty much just doing the forward prop again, but for a particular sample. And in the end, instead of computing the loss, we actually choose our prediction. We make our prediction. Okay, so the next thing I'm going to do, so this is for like one particular sample I evaluated. So what we want to do is actually do this for every single sample in our set. So I've written up some code here. I'm not going to go over it because it's literally the same exact code repeated for all samples. And I'm actually just going to copy paste this in the chat, which is being temperamental. Okay, perfect. So literally anyone who come up with this pretty quickly is just go over all the samples, calculate your predictions, find out how many of them are correct. That's it. And it's going to print out the final accuracy of our model at the end. So our model was trained for only like 1 epoch, maybe 1.5 epochs. So it shouldn't be very good, but actually it should give a pretty decent accuracy. If you train for like 10 epochs, you're going to get like pretty great accuracy. Yeah, we already have like a 95% accuracy, which is pretty amazing. So neural networks are really powerful, especially when we have a good amount of data. Now, the next thing, right? We're done, almost done. So we have our beautiful model. It's trained nicely. It's got all these beautiful weights. Next thing you want to do is actually save these weights, because trust me, like if you've run a model for 1 week on a supercomputer somewhere, you've paid a lot of money, and then you got some amazing results, 99% accuracy. You come home, you're like really happy, and you click close, and all your weights disappear forever. You want to save your weights before you do anything else. Okay, you want to save your weights so that you can use them again. And the way you do that is torch.save, and you access your model, and you access something called the state dictionary. So it just simply records all of the values in your model. And I'm going to save it in, let's say, /mymodel.pt. PT refers to, of course, PyTorch. So it just saves your model at this file. Okay. The next thing I do is I load the weights. Actually, let me make a comment entry here. Save the weights, and now we're going to load the weights. So 1 week later, your boss says, "How did your model do?" I'm going to say, "Okay, I'm going to pull up my model from my saved file." So the first thing I'm going to do is define a brand new model. I'm going to say my new model is equal to a new object with the same exact architecture. So these are completely random weights right now, but it's going to have the same architecture, of course. And yeah, so we're going to have the same exact architecture. And what we're going to do, we're going to first load our weights. So we can say torch.load at this file location. So this contains all our weights. And actually, let's put it this way. So model weights. So I'm going to load all my weights. And I'm going to say my new model, please load the state dictionary, which is model weights. You see? So all it's doing is it's saying, take these weights and stick them into the model. That's about it. And you get a nice confirmation message that all the keys were matched successfully, which means the models were actually compatible with each other, and that all your weights have been successfully loaded. Okay. So are there any questions about loading or saving weights? Or any questions about anything previously as well? Okay. Is everyone good? I'm wondering, did everyone manage to catch up? Okay. Awesome. So that's the end of our workshop. So thank you all so much for coming. We have a feedback form as usual. Please fill it up. We really appreciate the feedback. Oh, awesome. You all managed to catch up. That's great. So yeah, please fill out a feedback form, and thanks for coming. We have office hours right after this on the Discord channel. Feel free to attend those. But yeah, we really appreciate you guys' feedback, by the way. So please fill out the feedback form. It'd be really awesome.
Yeah, thank you all for sticking with us. I know it was a kind of long workshop.
Yeah, absolutely.
Thank you.
Yep.
All right.
Yep. See you guys.
I'll see you guys.
Yes. You want to end the recording, Jenson?
Oh, yeah.